Hello students, in the last class I have started the new chapter boolean algebra. So we will continue that chapter. Today in this class we are going to see two topics. One is logical operators, second one is logic gates. In the textbook actually we are having this one, evaluation of boolean expressions using truth table in between the operators and logic gates. So it would be better to consider logic gates after the operators. So that's why I am skipping this one, evaluation of boolean expressions. We will see that one in the next video class. So in here now in this class we will see logical operators, immediately logic gates, and some definitions of truth table, tautology and fallacy. So first we will see the operators, then here I have written logic gates. So when it comes to operators, you people have already learned about the logical operators in the first year in computers, C++ programs, and in mathematics chapter is mathematical reasoning. What the difference here is that the symbols we are using here are different than the symbols we already used in maths as well as in CPP. In CPP program, of course, logical AND means the double ampersand symbol, logical OR means double pipeline, and the logical NOT or NOT operator, it's going to be exclamatory symbol. So those symbols we have used and we will continue to use them even in second year CPP program whenever we require them. So compulsorily we have to use those symbols when it comes to CPP programs. Okay. But what other symbols you know in mathematics in the last year we have used for logical AND. Okay. The operator symbol we have used like that, and we used to call that one as conjunction. For OR operator we use the symbol like this and it is called disjunction, and for the NOT operator you are using this symbol, negation symbol. So only the symbols are changing. Here we are preferring dot symbol for the AND operator plus a symbol for OR operator. So we have used these one in mathematical reasoning and we are using these in C++ programs. So what about the NOT operator? Here we are having that symbol also, this one, negation symbol, which is actually tilde operator, and so that one we are using anyhow. Plus we are having two more symbols here, this bar symbol and this single quote. So three symbols are there in this chapter for the NOT operator, and usually we are preferring this one, first symbol, that is bar symbol. So when we see the operators, symbols are changed here in this boolean algebra plus dot, and there are three symbols. Moreover, the property of those operators are same. Okay. So if you consider this first operator AND operator, the property is what? It is going to be true. Answer is true if all are true. Okay. See here, if we consider x and y are the two operands, then for these two operands, when you apply the AND operator, you can write it normally in this fashion: x and the actual word itself we can use x and dy, or we can use here in this boolean algebra as x dot y, or simply just x y. Okay, so it's understood. Dot is not necessary, it is implicit. Even if you just write x y, it's understood that it is going to be x logical AND or AND operator here, then y. So we will prefer this one, even dot is not necessary. So considering these two variables or operands, then if you go for the answer or the result concerning the truth values of the variables, So truth values are going to be either true or false. We can write it in terms of 0 and 1. So these are the combinations we are going to get when there are two variables. Okay. So both are 0, 0, 1, 1, 0, 1, 1. So here the answer x plus y. Okay, it's actually x dot y, or just we can write it as xy. Okay. So x and operator y is going to be true if all are 1. Otherwise it is 0. So both are true or all are true, then it is true, otherwise it is false. And this we can say AND operator performs logical multiplication. So it's not normal multiplication, it's a logical multiplication. Though this logical multiplication exactly matching with the normal multiplication. Where in normal multiplication what happens? Anything multiplied with 0 is going to be 0. But don't consider in that way, it is different logical multiplication. Here we are talking about the true and false, and don't think about 0 and 1 because it's about the boolean algebra. So true or false are there. So when all are true, then the answer is true. Okay. So this is a property, answer is 1 when all are 1. Now come to Venn diagram. So Venn diagram, last year mathematics you have used here in the chapter sets. So there in the sets why we have these Venn diagrams. Venn diagrams are used to show the relationships between the sets. So wherein we are using rectangular box for the universal set and circles for subsets of the universal set. So now the Venn diagram for this AND operator. So when AND operator is used in an expression, boolean expression, so it is going to perform some operation. So what about that operation now? So two variables we are considering, or two operands. Say one circle is x, the other circle which we have to show in this fashion, it is overlapped with x. So this is y, this is x, and we are talking about the AND operation. So AND operation is quite similar to the intersection of two sets. Okay. So in an intersection of two sets, which area we are going to shade in the Venn diagram? This is the area. This area we are going to shade because the ones have to be present in both x and y. So this is the common here. So if it is present in both, then only answer is 1. If it is present only in x or only in y, answer is not going to be true. So that's why only this area we are going to shade. So the Venn diagram which we are used for x intersection y, two sets. That same Venn diagram is the diagram for AND operation. So next moving to OR operator. Okay, so OR operator performs logical addition and the symbol is plus. So again, if you consider any two operands like x, y, then we can write it as normally x or y, or you can use the symbol x plus y. Then the truth table, and in the truth table you can observe answer is false or answer is 0 when all are false. Otherwise it is going to be true or 1. So this is the property. Answer is 0 if all are 0. Otherwise it is 1. So this is a logical addition. So don't consider it as 1 plus 1 is 2. So when in normal addition it is so, but here it is about only the logic or binary. So the answer must be either in true or false or 1 or 0, not any other symbols. So it is going to be logical addition. So OR we are using. So answer is 1 and both are 1. Even when one of the operand, if it is 1, then answer is 1. It is 0 only when all are 0. So AND operator, when it is in operation, it is going to perform logical addition. So what about the Venn diagram? Venn diagram of OR operator of this OR operation is the diagram of the union of two sets. So this is universal set. Now again, if you go, one is x, the other one is y. So this is only x, this is only y, this is x as well as y. So when two sets are there, the elements which are present in both the sets we are going to write here because they are common, present in both sets, and the elements which are present only in y we are going to write here, elements present in only in x we are going to write here. So now when it comes to logical operation, addition operation, when one is present in any of the operand, if not in both, then also answer is true. So that's why all the areas we have to share here, only x portion, only y portion, as well as x intersection y. So all the three areas have to be shaded for the OR operation Venn diagram. Okay, so this is the Venn diagram which we have seen for the union of two sets. Okay, now coming to the NOT operator. NOT operator is a bit different because it operates on only one operand. Okay, so it is a unary type. Here I have written unary or singular. Okay, so remember unary or singular because NOT operator operates on only one operand. So that's why we are considering only one variable like x. Okay, here we have considered 2 because minimum we require 2 here. Here only 1. Okay, so if x is the variable, then its complement or the NOT operation can be written using this symbol bar, x bar, using the negation symbol, negation of x, or this single quote x dash. Okay, x bar, x dash, this tilde operator x. So in any way you can write, but usually we are going to prefer this x bar. Okay, so what about the operation? It's complement operation. So what do you mean by complement operation means the existing value is changed to the other value. So property is what? It reverses the existing status. So suppose if x is 0, x bar means is 1. If x is 1, x bar means 0. So what about the Venn diagram now? Venn diagram is similar. It is our negation operation which we are using, or the complement of set. Okay, if x is a set, then what about the x bar means it's outside of circle. So that is a Venn diagram for the NOT operation, or you can say for the NOT operator. Okay, so this is about the logical operators, and meanwhile we have to see the definitions of truth table, tautology and fallacy. So already we have seen the truth table here. So what actually the definition of truth table? Okay, so truth table is a table where it is having all possible input values with their corresponding output values. Okay, so all possible values for the inputs or for given variables and their corresponding results. So this is about the truth table. And what about the tautology and fallacy? So tautology is the case when in the resultant column, means after the operation, whichever will be the operation, and or not, or a combination of many operations. So finally the resultant column, suppose if it is having all as 1 or true, then it is called tautology. So fallacy means if the resultant column is all are 0, then we can say that particular expression or operation as fallacy. Suppose here if you got as 0, for example, then here you can see all are 0. That time you can say this particular operation or the expression xy as fallacy. So it is not the case. Here actually we are having 1. So as an example, say if x is the variable. Say suppose if you consider this expression, x logical OR operator and x bar. So what happens? X plus x bar. So if you consider as 0, x bar is 1. If x is 1, x bar is going to be 0. Then x plus x bar means 0 plus 1, 1 plus 0, logical OR operation. So from this truth table, if you see even in one of the variable is having 1, answer is going to be 1. So here in this case you have 1. In the second row you are having 1 here. So if not both as 1, at least if you have one of the value as 1, the output is going to be 1, and here also it is 1. Now this is the resultant column. This is the resultant column for this x plus x bar. Here we are seeing all are 1. So this is the tautology. So for the fallacy, we can consider a simple example is like this. Say x into x bar means logical AND. So this is about the x column, this is about the x bar column. So possible values for the inputs for the given expression. So x into x bar. So logical AND is there. So logical AND property is what? If all are 1, then only it is 1. So it is 0. Here also it is 0. So all are 0 in that resultant column. So that's why it is an example for fallacy. So what exactly fallacy means? If the result of the expression, if it is always 0, then that expression we can consider it as fallacy. If the result of the expression is always 1, then that expression or that operation is called tautology. So these two are the special cases, tautology and fallacy. So we have seen these logical operators and or not, and we have seen the definitions of truth table, tautology and fallacy. And now we will go for the basic logic gates. And the basic logic gates are and or not. And of course, when you see this word here, basic, it gives a hint that there are some more gates. Yes, there are some more gates. Those gates are called derived gates. Okay, so these three and or not are basic gates. We are learning them here itself, whereas the other type of gates, derived gates, that we are going to learn in the next chapter. Okay, this is chapter number 2, Boolean algebra. In the next chapter, 3rd chapter, chapter name is logic gates. Okay, chapter name itself is logic gates. In that logic gates chapter, we are going to see 4 more gates under the heading called derived gates. So there we are going to see 4 gates. Now we will see only basic gates. So in a basic gates we are having 3 and or not. Okay, so just now we have seen and or and not operator and the operations involved in those operators. Now we are looking into the gates and or not gates. So we are calling them as logic gates because they are working on only 2 values 0 and 1. And moreover, we are talking more about electronics when we take up the logic gates. So other name for the logic gates is electronic circuits, or you can say logic circuits. Okay, so there here I have written, okay, here I have written electronic circuits or digital circuits. So logic gates, even it can be asked as define the logic circuit or define the digital circuit. So whether it is logic gate or electronic circuit or digital circuit, all are same. But here we are talking about the electronics. In the computers, these logical operations or Boolean operations can be performed by using logic gates or electronic circuits. So it is somewhat theoretical way of discussing the operations and not. Here we are talking about the operands, the variables, and true, false. But when it comes to electronic side, it is actually the signals, input signals. It is not about somewhat like true or false. Here we have to say high volts or low volts, or else we can say 1 and 0 here also. Okay. So when it is 1 means what? It is actually high volts. In the last video session I told you when at the electronic side it is about high volts and low volts. That is the two differences those electronic equipments are going to identify, and our computer is electronic device. So these operations can be implemented by circuits, electronic circuits. So what about the definition of logic gate? Okay, or say electronic circuits. So it's an electronic circuit having one or more input signals and an output signal. Means what? Electronic circuit or logic gate is having one or more, means greater than or one or more input signals, okay, and an output signal, means only one output signal. So whichever the gate or whichever the circuit we are going to consider, whichever means what? Here we are going to see 3 gates, and in the next chapter we are going to see 4 gates. So whichever the gate it may be, it is going to have one or more input signals and only one output signal. Okay, but except NOT gate. So NOT gate is a special gate. It is a unary operator. We have seen when we talk in terms of operator, it is unary type operator. It operates on only one operand. So in the same way, when it comes to NOT gate, it is going to have only one input signal. So only in the NOT case, okay, NOT gate, only in the NOT gate, input side is compulsorily equals to 1, and output side anyhow we already know in general output is going to be 1, whichever may be the gate. But input side it is changing only in one particular gate, NOT gate. So in the NOT gate we are going to have only one input signal. In all other gates, okay, leaving the NOT gate, in all other gates, OR and in these derived gates, we are going to have more than or equals to 2 input signals and 1 output signal. Okay, so you have to remember this one. The normal definition of electronic circuit says that one or more input signal and output signal. But when it comes to NOT gate, only one input signal, one output signal. Remaining in all other gates, leaving the NOT gate, it is more than or equals to 2 and an output signal. So in general, we have to say this when we are writing about the definition of electronic circuit. So one or more input signals and an output signal. So when we are talking about the AND gate particularly, so we can say it is having 2 or more input signals, all other, okay, 2 or more input signals and an output signal. And output signal is going to be 1 if all the input signals are 1. So this is the definition of AND gate. So it is a circuit, electronic circuit having 2 or more input signals and an output signal. And the output signal is going to be high when all the input signals are high. Or else output signal is 1 when all the input signals are 1. So that's why we are calling it as AND gate. Okay. So as I told in the examination, you have to be a bit careful whether it is AND gate or AND operator. So carefully you have to write the answer. So when you are writing about the AND gate, you write the definition first. So as I told you, output signal is 1 and all the input signal is 1, and it's an electronic circuit having 2 or more inputs and 1 output signal. And you write the symbol of AND gate. So here I have written 3 symbols. This is the first symbol, If you have considered 2 or more means minimum you should have 2 input signals. More means there is no limit. So just here I have indicated one more AND gate symbol having 3 inputs x, y, z. Like this there is no limit. You can have n number of input signal and an output signal. So this is a 2 input. So the symbol is capital D letter. So minimum you should have 2 and an output signal. When you have 2, you just give some names, and this is an output. You can give one more letter to that side. Say if you use this x, y, here output. If you are identifying by the letter F, then you can say it is x into y. So here you can say F equals to x into y. Suppose 3 input signal if you are showing, then you go for one more line here. You say it as a z. So likewise there is no limit. You can go for m number of input signals and an output signal. So 2 input signal symbol, 3 input symbol, this is an input symbol. So this is the logic gate of AND. Actually the actual electronic circuit is going to be different. It is all about the transistors. So in a processing unit, in a CPU, we know already it is made up of with electronic components, and millions of transistors are there in a CPU. Okay, so here this AND gate, which is usually represented like this, it is just a block diagram. It's a higher level representation of AND circuit. Actual circuit is going to be like this. So this is actual circuit of AND gate. It is going to be somewhat like this. So we are just using this symbol. It is not required for us. So when you go for higher studies, you may study that one. Here actually these are the transistors. Okay, this is one transistor. This is another transistor. They are connected in that fashion. So these are the resistance. Voltmeter, this is a battery. Okay, so these are the input signals x and y. So when we are applying signal here, say for example plus 5 volts, and here say suppose 0, or else if you consider one by one, say you are not applied any volts, means low volts, 0, 0. So what happens? Here the battery is there, then these transistors, say transistor 1, this is transistor 2. Okay, so here what happens? Current won't pass through this transistor. So this transistor, it is actually going to be identified by as base, this one as emitter, this particular line as collector. Okay, so when 0 volts is here, no potential difference is going to be created. So no potential difference means say PD equals to 0. So no potential difference, so current won't pass through this transistor. So when you see here in voltmeter, you are not going to see any deflection. So it is going to be 0. So when both are 0, output signal is again 0. Say suppose 0 and 1. So this is 0, this is 1, means you have applied some nearly plus 5 volts to this line, Y line. Okay. So here it is 0. Current won't pass through again through this transistor, because there is no potential difference at this transistor. So it acts like a off switch. Okay, this is of course on, but current stopped here itself. So no question of passing through this transistor and completing the path. So again we are not going to see any voltage difference in the voltmeter. Okay, again it is going to be 0. If you reverse, so this side if you are supplying voltage, this is 0. So current is passing through this X line, and no, here 0 it is, no volts, no current here in this line. So that time what happens? This one, since it is 1, means voltage is applied. So here we will see some potential difference. So due to that potential difference, what happens? Current passes through this transistor 1, it passes through this transistor and comes up to transistor 2. Means what? It is now acting like a on switch. Okay. But what happens here? No volts. Okay. So PD, potential difference is 0. So again current 1 passes through this transistor. So that's why you are not going to see any difference in the voltmeter, any change in the voltmeter. So that time also it is going to be 0. So when you apply voltages to both X and Y signals, okay, so when both are 1 1, means both are around plus 5 volts, then potential difference occurs at the transistor 1 as well as at the transistor 2, means both the transistors are now on status. So that's why sometimes we are going to see that transistor works as a on off switch. Okay, so that's why now transistor 1 and 2 both are in on status. So potential difference is occurring across T1 transistor and transistor 2. So current passes through transistor 1 and again passes through transistor 2, and it continues, and now we are going to see a voltage difference. So a deflection in voltmeter we are going to see. So that is what it is 1. Okay. So this is actual circuit implementation having the transistors. Okay. But don't worry, it is not there for our syllabus at PUC. Okay. So this is not actually the circuit, that is actually the circuit, but we are just using this symbol to indicate AND gate. Okay. Moreover, these gates AND or not, again you are going to learn in physics this year, that is in the same chapter, semiconductor electronics. So again you are going to see these three. So anyhow, now, so we have seen about the AND gate. So this is an input AND gate. So first you write its definition, then symbol, then you write it to table. To table, again you can use the same to table for the AND operator. You write again in answer. So when it is for 3 marks, better what you can do, even write the table for 3 input signal. Okay. So this is a 2 input signal. Here you can write. So likewise you can write 3 input signal. So when it comes to 3 input signal, here we are going to have 3 variables. So how many possible combinations of zeros and ones we can write? It all depends upon this formula to the power n, where this n indicates the number of signals. So here in this case is 3. So to the power 3 means 8 possible combinations of zeros and ones we can write. So they are 0 0 0 0 1 0 1 0 0 1 1. 1 0 0 1 0 1 1 1 0 triple 1. So in the last year I told you, you write the combinations of zeros and ones in this order. So it is some standard order. Basically we have written these possible combinations of zeros and ones in the order of their decimal equivalents and in the increasing order. So 000, its decimal value is 0, its decimal value is 1, its decimal value is 2, its 3, 4, 5, 6, 7. So each combinations of zeros and ones, they are actually representing the decimal values in increasing order. So decimal value zeros binary we are writing first, then decimal value ones binary combination we are writing, then decimal value twos binary combination, like this we are writing. So it's about from 0 to 7. Now AND operator property is same. If all are 1, then only answer is 1. Otherwise it is 0. So here 0. All are 0 except the last case. Okay. So here only we are going to see signal. Means when it is of 3 input signals, say here, when you apply high volts for all the inputs, then only you can see a signal at the output side. Otherwise, it is going to be 0 at the output side. Okay. Now we will go to this OR gate. So OR gate, its symbol is this one. So here also actually the electronic circuit is different. So as we have seen the transistor circuit for AND gate, in the same way transistors are used for the OR gate also. In a different way they are going to be connected. So anyhow that is not required for us. So this symbol is enough for us. So this is a symbol for the OR gate. How it is? It is not actual triangle type arrow mark. So it's curved lines. Curved lines. All the 3 lines are curved here. Here you can indicate the number of inputs. Minimum you should have 2 for the OR gate. 1 output signal anyhow. So this is 2 input signal OR gate. This is 3 input signal OR gate. Likewise you can have n number of input signals. Okay. So here also you first write the definition. Suppose if there is a question on OR gate. So what is the definition? It is an electronic signal having 2 input signals or 2 or more input signals and an output signal. And output value is going to be low or 0 if all the input signals are 0. Okay. Then you write the symbol 2 input, 3 input, n inputs, and then you write the truth table. So when it comes to truth table, compulsorily you write for the 2 input signals truth table. Further, you only decide if it is for 3 months, better you write even 3 input signals truth table for OR also. So this is the same truth table. You write the for OR gate. Only thing is instead of writing x, y, z, what you write? X plus y plus z. And the property of OR gate says that it is going to be 0 if all are 0, otherwise it is true. So that's why what happens in the output side, you are going to get 0 only in the first case. So all the remaining cases, the output is going to be 1 in case of OR. Okay. So only 1 0 when all are 0. Then the remaining cases it is 1. Now coming to last one, NOT gate. It's a unary operator. Okay, unary operator. So when it comes to electronic circuit, this is a symbol we are using. Again, it is going to be constructed by the transistors. Okay, then this is the symbol, arrow mark followed by circle. Okay, small circle. First you write the definition, NOT gate definition. It is an electronic circuit having only 1 input signal and an output signal. So output signal is reverse of the input signal. Okay. Then you write the symbol X. Here it is the output side. It is X bar, complement of X. Then you write the truth table. When it comes to truth table, only this is the truth table because here there is no case of more than 1 signals. Okay. So this truth table again you write here when it asks for the NOT gate. Okay. So this is about today's class. We have seen the logical operators. Immediately we have gone for the logic gates, and we have seen the definitions of truth table, topology, and policy. This one, evaluation of boolean algebra, boolean expressions using truth table. That one we will see in the next class.